Hi, this is Ms. Basin, and in this screencast we're going to talk about precipitation reactions, which is section 4.2. So when you have a reaction that forms an insoluble product, this is called a precipitation reaction. Now up to this point we have known this as a double replacement reaction. So a precipitation reaction is a specific type of double replacement. So when you have two aqueous solutions and they react, a precipitation reaction is one that results in a precipitate, which is an insoluble solid. So this is an example, and we've probably seen this one before in class, but this is lead nitrate and potassium iodide, and that precipitate that you're getting there is lead iodide. So to determine which of the products in this double replacement reaction forms a precipitate, we're going to follow the solubility guidelines. So when we talk about solubility, what that means is how much of a substance can be dissolved in a given quantity of solvent. So it's a little bit more complex than just will it dissolve or not. Solubility is defined by a certain amount being dissolved or being able to be dissolved in a certain amount of or a certain volume of solution. So the definition of insoluble is if it has a solubility of less than 0.01 moles in 1 liter. So if less than 0.01 moles of the substance, which is a pretty small amount, will dissolve in a liter, then we classify that as being insoluble. So the way that we predict this is we look at what are called the solubility rules. So there are experimental observations that have led us to these guidelines. So the activities in class today, you came up with these solubility rules by yourself by reacting all these things and then looking for those patterns. So the general patterns that you probably figured out already is that nitrates are soluble. So anything that has nitrate in it, those are going to be soluble, because if you notice the way this table is written, it's listed as soluble versus insoluble, and then over here are the exceptions. So nitrates have no exceptions, acetates have no exceptions. Ammonium ions are also not on here. Those do not have exceptions either. Okay, so then you notice that below that there's a list of compounds that for the most part are soluble, but then there's some exceptions. So there's an example there. If you have chlorides, most of the time those are soluble unless they're combined with silver, mercury, and lead. Bromine, mostly soluble unless it's silver, mercury, lead. So if you notice, the exceptions are a lot of times things that are similar. So silver, mercury, lead come up a lot. And then down here with the sulfates, usually soluble, but again, unless it's strontium, barium, mercury, lead, those would then be insoluble. Things that are insoluble would be sulfides, carbonates, phosphates, hydroxides, and then again, you have some exceptions there as well. And when we go through these, you'll start to kind of get the feel for predicting what's soluble and what's insoluble. You'll start to see the same things come up over and over and over again. Okay, so let's look at a couple examples here. So it says to classify the following as soluble or insoluble. So this first one, the sodium carbonate, is soluble. So if we look down at our list, carbonates are usually insoluble unless they're combined with ammonium ions or alkali metal cations, which is what this case is here. If we look at our next example, lead sulfate is insoluble. So on our list, sulfates are usually soluble unless they're with strontium, barium, mercury, or lead, which this one is here. Cobalt hydroxide is insoluble, and that follows the rule that hydroxides are insoluble, and cobalt is not one of the exceptions. Barium nitrate is soluble, and that's because all nitrates are soluble. And then the last one, ammonium phosphate, that one is soluble, and that's because of that ammonium ion. And again, you'll get better at this and you'll be able to predict a little bit easier once we do lots of equations and lots of reactions. Okay, another classification, and this is really a broader category for what we just talked about. But these are our double replacement reactions. Now there's a couple other terms that at this level we can use for this, but this is generally speaking a double replacement reaction. So here we have, you could also call it a metathesis reaction, an exchange reaction. We called them double replacement reactions before. They could also be called double displacement reactions. That's just another term that's thrown in there. So when we have this, what happens is the ions transpose or they exchange with the other. A lot of precipitation reactions are follow this pattern like we just said, and then another type we'll learn about later are acid-base reactions. Those also follow this pattern. So if we look at our example here, we have silver nitrate and potassium chloride. So on the other side, the potassium takes the place of the silver nitrate. Silver takes the place of the potassium, and then the chloride switches out with the nitrate. So we end up with silver chloride and sodium nitrate. Now if you notice here, these are our two substances. This is where our solubility rules will help us. So what they're doing then is they're helping us figure out which one of these things is a solid and which one is still aqueous. So this particular one, we knew silver chloride was a solid because nitrates are all soluble. Okay, so let's look at a couple examples here. This one says, predict the identity of the precipitate that forms when solutions of barium chloride and potassium sulfate are mixed. And then we're going to write the balance equation for the reaction. So we're going to do this just like we did before. So we've got barium chloride, which is BaCl2, plus potassium sulfate, so K2SO4. So we're predicting the products just like we've always done, where the ions switch places. So we have barium sulfate, and that's a +2 -2, so that's good the way it is. And then we have potassium chloride, which is a +1 -1. So we end up with that, and we have to balance it. So we have to put a 2 in front of the KCl. So that is our balanced equation. So now what we're trying to figure out is which one of those two things is our precipitate. So again, like I said, usually one thing stands out, and that helps you decipher between which is a precipitate, which is aqueous. So in this particular case, chlorides are soluble, with a couple exceptions, and potassium is not one of those. So we know that that's our aqueous product in this equation, and then our barium sulfate would then be our solid. Now when we're writing our formulas out here, that little s stands for solid and not soluble, which is a little bit confusing. So when you're labeling what state the different things are in, this s, the substance that forms a precipitate, is labeled with an S for solid. Okay, so here's another example if you want to see another one. So we have iron sulfate and lithium hydroxide, and these are mixed together. So again, double replacement reaction here. So iron combines with the hydroxide, and it's iron 3, which we can tell from over here, and then lithium sulfate, Li2SO4, because lithium's a 1, sulfate's a 2, or sulfate's a 2. Our next step would be to balance this. So I would need a 6 right there. So this is a 6 in front of the lithium hydroxide, 2 in front of the iron hydroxide, and then a 3 for the lithium sulfate. So then my last thing to do here is figure out which compound precipitates. So if I look at those two and I refer back to my solubility rules, I see that my lithium sulfate will be aqueous, and then my iron hydroxide will end up being my solid. Okay, last example, if you want one more, it says, will a precipitate form when barium nitrate and potassium hydroxide are mixed? Okay, so barium nitrate, so BaNO3, 2, and KOH gives me KNO3 and BaOH2. Okay, so if I look at that, and then I need to go ahead and balance it. So I need a 2 here, and I need a 2 over here. So if I then go and check my solubility rules, both of these end up being aqueous. So this one is aqueous, and so is this one. So for this particular reaction, this is actually not a reaction at all, because all you ended up with are aqueous solutions of the same ions that you started with. And we'll talk a little more about that in the next couple sections here. But both of these ended up being aqueous, so there is no precipitate. So when you mix two things together, you're not always going to get a precipitate. It all depends on your solubility rules. Okay, so now we're going to look at a couple different formats for writing equations. So we can look at things called net ionic equations. So instead of looking at the overall equation, we can just pay attention to exactly what is present and exactly what is changing. So instead of writing the overall equation like we have been doing, we're going to break it down so that we're only showing what's actually interacting in a given reaction. So what we've been doing so far is called the molecular equation. So when you write out the whole compounds for the reactants and products, this is a molecular equation. So this is what we've been used to doing so far. Now what we can do, now that we know what happens when things dissociate in solution and we know which things do dissociate and which things don't, we can show what's called an ionic equation. So what this does is this gives us a better picture of what's actually going on in the reaction. So if we take that one that we just looked at before, we notice that silver and nitrate are split up because that's an ionic compound. Potassium and chlorine are split up, again because that's an ionic compound. And then for the products, we have silver chloride as a solid. So if you have a solid, a precipitate in the solution, it doesn't break apart. That's going to be sitting at the bottom of the beaker. And then the potassium and the nitrate break up because those are soluble. Okay, so once you have an ionic equation, then you can look at what's called a net ionic equation. So what the net ionic equation then does is it shows us things that didn't change and we get rid of them. So when we write our overall net ionic equation, we eliminate things that are called spectator ions. So in this case here, we started with the silver, the nitrate, potassium, and the chloride. The silver and the chloride formed a solid. Then we still had the potassium and the nitrate left over. So anything that's the same on both sides, and this will be a little bit easier to see when we work one of these out and it's all in one place. The potassium crosses out because it's the same on both sides. The nitrate crosses out because it's the same on both sides. So for us to show the overall net ionic equation here, we get rid of those spectator ions and we're left with that overall net ionic equation. So the steps for doing this is to first start by writing a balance equation. So you're going to write the equation out just like we've always done. Then you're going to dissociate all the strong electrolytes. So using the rules that we talked about before, if it's a strong acid, if it's an ionic compound, you're going to dissociate those and spread those out into their ions or break those up into their ions. Then you're going to cross out anything that remains unchanged from the left to the right. So if it's the same form on the left as it is on the right, then you get rid of it. And then you write the net ionic equation with the species that remain. Okay, so let's go through and do a couple examples here. And like I said, this will make a lot more sense once we work our way through a couple of them. Okay, so this one says, write the net ionic equation for the precipitation reaction that occurs when calcium chloride and sodium carbonate are mixed. So we're going to start this just like we always did, where we have calcium chloride, so CaCl2, and sodium carbonate, Na2SO4. I'm sorry, carbonate, Na2, CO3. There we go. Okay, just like before, switching ions, they're exchanging ions, so I end up with calcium carbonate and sodium chloride. Okay, and then we balance it, just like we've always done, so I need a 2 for that sodium chloride. Okay, so this is our molecular equation. Now, our next step is to create the ionic equation. So I'm going to go through, and actually before I'm going to do that, I need to figure out which of these two things over here is my precipitate, which of my products is my precipitate. So sodium chloride, the chlorides are soluble, so we know that's our aqueous, so that means our calcium carbonate is our solid. So, and that's real important to label before you start breaking stuff apart because the solids don't dissociate. Okay, so now we can go back to our beginning over here. So calcium is a +2 plus 2 Cl minuses. Okay, so look back up here and see how that works. So when this dissociates, What those subscripts mean is they tell you how many of each ion are there. So there's one calcium ion, which we know is a +2, and there's two Cl- ions, so we put the 2 in the front, and it's a -1 charge. Okay, now we move to our next one. This is also an aqueous solution. So I have two Na pluses, plus 1 CO3 minus 2. So they're breaking back apart to the ions they were before you crisscrossed the charges and wrote the compounds. All right, now on the other side, my solid stays together. So CaCO3 stays the way it is. And then my sodium chloride, now if I have a number in front, that goes to everything in the compound. So I have 2 Na plus and 2 Cl minus. Okay, so now this is the point where I'm looking to see if I have things that haven't changed on both sides. So sodium is the same on both sides, so I can get rid of it. Chlorine is the same on both sides, so I can get rid of that. So now all I'm left with is the reaction that produced the precipitate. So my net ionic equation then would be Ca plus 2 plus CO3 minus 2 gives me CaCO3. So what that shows me is that shows me what's actually reacting in this whole equation. So those chlorines and sodiums, those are my spectator ions because all they're doing is hanging out in that solution. They're not reacting, they're just watching what else is going on. So that's why they call them the spectator ions. And then the true reaction happens between the calcium and the carbonate to form the calcium carbonate. Okay, so another example problem. This one I want to know what is the net ionic equation for the reaction that occurs when I mix silver nitrate and potassium phosphate. So just like before, I'm going to start with my silver nitrate and potassium phosphate. So AgNO3 plus potassium phosphate, K3PO4. Now when they give you information like this, usually they're going to tell you that those original solutions are aqueous. If they don't tell you they're aqueous and you know they're compounds like that or they're solutions, like if they leave out the word aqueous, you can make the assumption that they are aqueous solutions. Okay, then we're going to switch our ions here. So I end up with silver phosphate, so Ag3PO4, because this is a +1 minus 3, and then sodium nitrate. Okay, next step, balance this. So I need a 3 here and a 3 over here. Next step, figure out which one of these two things is my precipitate. So again, if I look at this, nitrates are soluble, so I know that's aqueous. So that means my silver phosphate is my solid. Okay, step 2 is to now break everything up into its ions if it can. So my first one is my silver nitrate. So remember that 3 in front goes to everything. So I have 3 silver ions and I have 3 nitrate ions. Then go to my potassium phosphate. So that 3 means there's 3 K pluses plus 1 PO4 minus 3. Other side, silver nitrate's a solid, so it all stays together. Or I'm sorry, silver phosphate is a solid, so it all stays together. And then again, that 3 goes to everything, 3K plus, 3NO3 minus. Okay, last step, second to last step. Look and see which ones are the same on both sides. So I have a potassium 3K plus here, 3K plus here, and if you balance the equation right, you should have the same number of ions on both sides. So if for some reason you ended up with different numbers of the same ion, then I would go back and check your balancing. Okay, the other thing that's the same are my nitrates, so those are gone. So then last step is to write out my net ionic. So 3Ag plus PO4 minus 3 gives me Ag3PO4. So then that's my net ionic equation.